Welcome to The Explainer. Today, we're diving into something pretty cool, the hidden geometry behind how AI actually reasons. All right, here's what we're going to cover. First, we'll look at the big problem, the incomplete web of knowledge. Then we'll check out a couple of really clever solutions, one called TransE, and what happens when that simple idea fails. That leads us to RotatE, a more complex rotation. And finally, we'll see how this all fits into building a smarter graph and ultimately a smarter AI. Okay, first up, the incomplete web of knowledge. Before we can get into the solutions, we really have to get our heads around the massive challenge these AI models are trying to solve. So think about this for a second. How does the computer know that my mother's husband is the same person as my father? For us, that's just obvious, right? But for a machine, that's a huge leap. It requires a kind of reasoning. And to do that, it needs more than just words on a page. It needs a map. And that map is what we call a knowledge graph. It's basically a giant web of facts. Each fact is stored as a super simple three-part piece of information: a head, a relation, and a tail. So you'd have something like head, Albert Einstein; relation, winner of; tail, Nobel Prize. Simple, right? You connect the dots. But here's the catch, and it's a big one. These knowledge graphs are massive, but they are always incomplete. I mean, think about it. You can have millions of facts, but there are always going to be missing connections, just gaps in the knowledge. And those gaps are exactly what holds an AI back from truly reasoning like we do. So, the name of the game, the whole goal, becomes what we call link prediction. The big question is, can we use the connections we already have to intelligently guess the ones that are missing? Can we teach the AI to fill in its own blanks? All right, so how did people first try to solve this? Well, that brings us to our second section, TransE. And the idea behind it is, honestly, it's just so simple and powerful, a real first step in the right direction. Here's the big idea. What if we could represent every single thing, every person, place, concept, and every single relationship between them as a point or vector in a big imaginary space? Think of it like a giant map where things that are similar are close together, and the arrows connecting them, the vectors, actually mean something. And this led to the first big model, called TransE, which came up with this super elegant formula. H plus R is approximately T. What does that mean? It means if you take the vector for the head entity, add the vector for the relation, you should end up right next to the vector for the tail entity. It's just vector addition. And this is what it looks like. The relationship becomes a simple translation. You're just sliding from one point to another. It's so intuitive. You start at the point for Paris, you add the is capital of arrow, and bam, you land right on the point for France. It's beautifully simple. Okay, so TransE was a huge deal, a real breakthrough. But it wasn't perfect. This super simple linear way of looking at the world started to run into some problems, especially when things got a little more complex. So let's take a symmetric relationship. Think is married to. It has to work both ways, right? If person A is married to person B, then person B is also married to person A. So how does our simple slide across the map model handle that? Let's actually think through the math here. If H plus R is approximately T, then for our example, that means A plus R is married to vector gets us to B. But it also has to be true the other way around. B plus that same is married to vector has to get us back to A. So for that to work, what does our R vector have to be? And this is where it all falls apart. The only possible way for that to be true is if the relation vector R is just 0. It has no length, no direction. The model is forced to conclude that the relationship is married to means don't move at all. It basically erases the relationship's meaning entirely, a huge flaw. You know, if you actually lay out the capabilities of these models, you can see the problem really clearly. Here, you can see TransE just can't handle symmetry. Big red X. And you know what's funny? Other models that came along, like this one called ComplEx, could handle symmetry, but they couldn't handle composition, the whole mother's husband thing we started with. It felt like you were always trading one problem for another. You couldn't get a model that did everything. And this is where things get really elegant. It was time for the next big idea, a new kind of geometry. Let's talk about RotatE, a complex rotation. We're moving from just sliding points around to spinning them.
The big spark of inspiration came from this: Euler's identity. Now, don't worry, we're not going to do a deep dive into complex analysis. The only thing you need to know is that this beautiful little equation is the perfect mathematical recipe for describing rotation. It connects exponents and trigonometry and these things called complex numbers, and the result is a perfect way to spin things around.
And that gave birth to a new model, which they called, you guessed it, RotatE. So now, a relationship isn't a translation anymore, it's a rotation. The model says, take your head entity, H, and rotate it by the relation R, and you will land on your tail entity, T. And the difference in thinking is just massive. Look at this. On the left, that's TransE, just sliding points from A to B. But on the right, that's RotatE. We're now spinning things in a complex space. It's a much more dynamic, much more flexible way to represent these relationships. And check this out. This one simple change, from sliding to spinning, solves all of our old problems. That symmetry problem? Easy. A married-to relationship is just a 180-degree rotation. Spin from A to B, then spin another 180 degrees, and you're right back at A. The relationship vector isn't zero anymore. Inverse relationships? Just rotate the other way. And composition, our mother's husband problem? That's just adding the two angles of rotation together. It's perfect. It just works. So, okay, that's the cool geometric theory. But let's pull back and see how this actually helps us build a smarter AI. How do we get from this theory to a real reasoning machine? Well, it all fits into something called the knowledge graph pipeline. First, you have acquisition, which is just sucking up facts from text and data. Then comes the key step, refinement. This is where models like TransE and RotatE come in. They do what's called knowledge graph completion, or KGC, to predict those missing links and fill in the gaps. And finally, you have evolution, where the graph is constantly being updated. And this is the whole point. By predicting these missing links, we're not just playing a math game. We are literally teaching an AI how to infer new facts it's never seen before. It's how we give it the power to reason about the world in a structured, almost human-like way. Which leaves us with a really cool question to think about. We've seen that simple translations can model some relationships, and elegant rotations can model even more. So it really makes you wonder, what other fundamental geometries of knowledge are still out there, hiding in plain sight, just waiting to be discovered?